Hi, welcome to Mathematics with Tom. I am Tom, and today we are going to continue our discussion of the probability distribution. So we have taken a look. Let me review what we have done briefly here. We just took a look at a family with 4 children, and we realized that could happen 16 different ways. Then we decided that we wanted to quantify these results in terms of the number of girls in a family of 4 children. And we did that. We put it into this table here. This table is called a probability distribution, and that's where we're going to begin. So notice this, a few things. Notice this, properties. These are key, and none of them will surprise you. Properties. What do we have? One is, notice this, all the probabilities for any of those, that most they could ever be is 1, and the least they could ever be is 0. So if you saw an alleged probability distribution that had a negative probability, it would not be a probability distribution. Also, so that's one thing. One is the x's, these have to be numbers. I'll write it this way. Maybe that would look better. Is how about we put the x's have to be numbers. So we found a way to quantify b's and g's in terms of g's. So if you had a, b, c, and d in your x position, you need to go back and refine the way you describe your results so that they can be described numerically. Okay? Then what's the next one? Oh, this next one you always need to check is that the sum of all of the probabilities is equal to 1. And it does. It works here. But I want to show you this. So the example of the notation. And in statistics, we write it as I did here. The sum of the probabilities is 1. Well, what that means is add up all of the individual x's. So in our case, what we would say is you'd take the probability of x1. You'd take the probability of x2 plus probability of x3 plus the probability of x4 plus the probability of x5. And let's just check that. So that's 1/16. That's the x1 plus 4/16 plus 6/16 plus 4/16 plus 1/16. Let's see, that's going to be 10, 11, 50. Yep, and sure enough, we have 16/16, which is just the fractions way of writing 1. So this is a legitimate probability distribution. And I'd like to make a graph of it. Let's make a graph of it. We'll do this down below. And here's what the graph might look like. Oh, here, not what it might look like. Let's just actually make it what it would look like. Well, oops, that line is a little downhill, isn't it? So let's make it so it's hopefully pretty flat. We wouldn't want any of our data rolling off. Now, you could do this a couple of ways. One is that you could convert your sixteenths into decimals. I'm not going to. I'm going to just use these in sixteenths. So 1, 2, 3, 4, 5, 6. These are in sixteenths. 5, 4, 3, 2, 1. And this is going to be the probability of x. And over here, we're going to put our x's. Well, our x's are what? There's 0, 1, 2, 3, 4, and 5. Now, really quick, notice we're only having a family with 4 children, yet we end up with 5 different possible events. That's because you need to remember to count that 0 in there. That 0 matters. So I'm going to graph these. Let's do these in this nice, that yellow is just hard to argue with it. It's nice and bright. So, and all we do, it looks similar to a histogram, But all we do is we just draw a vertical line up to the right height. So the first probability of 0 is 1/16. So I would just draw a vertical line. Maybe make it kind of bold, up to 1/16. For 2, it goes up to 4/16. Well, that's over here. So this is going to be a line that looks maybe more like that. And we continue at 2. We're at 6/16. That's our highest point. So let's do that. Make it nice and thick. And then we're back down to 4/16. So I'm going to just use these little dotted lines so I can keep track of how high to draw. You don't have to use those, especially if you have graph paper. And then finally, I think I'm off by 1. Oh, 4. 4 goes right back down to 1. Should be right there. Okay. I think we're done. There is our graph of our probability distribution. So let's look at this. Now, if all of those vertical lines, I'm going to do another color for a moment. Like pink. If all of these spaces in between 0 and 1 were full, that there was numbers in there, I'd be looking at a different kind of data set. This kind of a data set where there's gaps between the x's, let me write this. This is a key note here. Since we have these gaps, meaning we just have these, in other words, all of our data is just in terms of counting numbers, or just any whole number or integer. This is called, this is discrete data. Discrete data. And all it means is discrete data can be counted. That's it. That's all it means. In the way that we counted the number of boys and girls, and we wrote it in terms of girls, we were able to count exactly what our data was. That's not always true. In some cases, in those pink cases over there, where if we had an infinite amount of data, then we call that continuous data. And continuous data comes from when you measure things. For example, if you gave me a caliper, I measured something, and then you used the same caliper and measured something, we might get slightly different results. And so we might record a different number. And if another person does it, they might get a slightly different number too. All those infinite little differences would mean you'd get a completely smooth curve. So continuous data comes from measuring. Okay, we are going to be talking about continuous data. I'm sorry, in the next sections. Right now, we're going to just focus on discrete data. Now, let's take another observation from our probability distribution is notice that most of the data was right there at 2. So let's calculate the mean and see if that matches with what we're seeing. Now, I'm going to just write mean, and then we're going to come back and do some revisions to this. So the mean equals, now if you remember, the mean just says you take all of the x's, you add them up, and you divide by the number of x's. Now I'm going to do this problem 2 ways. The first way is to derive the general formula for you, and the second way is just to get the number, because we'll need it, and it's just nice to have a numerical value. So let's take a look. What was our first data? Our first data were zeros. Okay, how many zeros did I have? I only had 1. So I'm going to multiply it by 1 plus. My next data were ones. Now I had 4 of those ones. I had 4 ones. And so I could write 1, all right, plus 1, plus 1, plus 1 plus 1. There. So I could write 4 ones like that. Or what I'm going to do to make that a little easier, cleaner even, if you will, is I'm just going to say, instead of adding all those, I'm going to say, well, that's just 1, and there was times 4 of those. Okay? Plus, our next data values were 2's. And how many 2's did we have? Well, let's come back up above and look. For our 2's, we had our 2's here. 2 girls. Oh, our 2 girls were these yellows. So I have 1, 2, 3, 4, 5, 6 different ways. So 6 different ways to have 2 girls. So times 6. Plus, if you look up above 3, that occurred 4 different ways. Plus, we could have a family with 4 girls, and that would only happen 1 other way. So I'm going to take that, and we're going to divide it by the total number of outcomes, which is 16. Okay. At this point, most of us would rush to the answer, and I would encourage us, so I'm going to write it over here to the right, and we get that out of our way. So it's going to be 0 plus 4 plus 12 is 16. 16, oh, another 16. That's going to be a 32 over 16, which is 2. And notice that 2, it looks pretty much like what we were seeing right there, that 2 is the mean of the data. Now, let's take a look closer at what we have. Okay, we have to uncondition ourselves to do this next step. Uncondition. So how do we do that? Well, what we do is think about this. All these years that we were adding fractions, we said if I had a problem like 3/7, let me write that a little off to the side more. If I had the problem of 3/7 and I added that to 2/7, our determination was purely to start with, was to get to the fact that that's 3 plus 2 over 7, because we have a common denominator, and write our final answer as 5/7, and then we could move on. Okay. Now, let's undo all of our learning. Or in other words, let's do it backwards. Where are we? Right now, our formula is about this stage. But I wanted to go backwards. I wanted to separate all the fractions. And when I do that, notice that the common denominator is 16 in every single one. So I'm going to write this as 0 times 1 over 16 plus 1 times 4 over 16 plus 2 times 6 over 16 plus 3 times 4 over 16 plus 4 times 1 over 16. Okay, now let's do something again. And here's what I want to notice. This is done by direction. Like I'm leading us to see what's going on. Because look at this. If I look at this 1/16 in here, and this 4/16 in here, and the 6/16 right there, and the 4/16 in this next one, and the 1/16 in this next one. Well, wait a minute. Where are those? Those are right here. Those are the probabilities of the individual events. So let's come back down and utilize this. Let's write this as 0 times 1/16 plus 1 times 4/16 plus 2 times 6/16 plus 3 times 4/16 plus 4 times 1/16. Wow, look what we can do. What was 0? 0, that was x1. That was the first data value. 1/16 was its probability, the probability of x1. Plus, Well, the 1, we said that's the data, that's x, the variable x2, and the 4/16 is that probability. So that's the probability of x2 plus 2, well, that was our x3. 6/16 is the probability of x3 plus, where am I at? 3, that was x4, and the 4/16 is the probability x4 plus x5 times the probability of x5. Wow, we've just done it. We've figured out how to write the mean for a probability distribution. And what it is it's the sum, and this is the general notation, it's the sum of the x's times their associated probabilities. And that is how we can find the mean of a probability distribution. Okay, I hope that helps. Thanks for watching.